So far we've been talking about different sensors, what is the need for sensors, just giving a perspective of what are the different properties of light that we could potentially exploit, and how to pick up different physical parameters like strain, pressure, temperature, and so on, using these properties of light. So now it's time to go on to see a few examples of these sensors. So let me just go ahead and try to give you a feel for how to do sensing based on these parameters. So let's first consider amplitude modulated sensors, and you would see in the common literature that these are either called amplitude modulated sensors or intensity modulated sensors. Both are typically the same. Amplitude, you are referring to the electric field amplitude, but you know that the magnitude of the electric field amplitude, the square of that, is what intensity is. So you can even look at it as intensity modulated sensors. So what do you see here? You see a kid that's playing with the television, it seems like, and clearly this is a video game that's running over here. So how is this person able to communicate with this television console? Or if you think about more serious thing, this is actually a hospital operating theater, and very sterile environment that we need to keep, and this person seemed to be referring to something on the screen over here, and trying to understand what's going on, maybe in the middle of a surgery, and so on. So what exactly is going on in these type of applications? How is an optical sensor useful in these type of applications? Well, these are applications that are called gesture recognition. Okay, so what is gesture recognition? Basically, I do this gesture, and then the computer should be able to say, okay, this is what this person is trying to gesture, and then based on that the computer might take an action. In this case, if the kid is actually throwing up, is throwing a punch or throwing a kick, then the computer should recognize that and project an image which is mimicking that action. So how does it sense this? Well, this is actually a very good example of intensity modulator sensor or an amplitude modulator sensor. What exactly is happening here? You have somewhere over this console, you have an infrared source. So infrared source is something that we cannot see with our bare eyes. Our eyes are able to see only the visible radiation, that's from 400 to 700 nanometers. But if you go to the near infrared radiation, something in the order of 900 or 1300 nanometers, you won't be able to see that. So imagine there is a source of light like this, and it's able to project a pattern of dots, okay, in the far field. If you are able to do that, and if you have an object in between the source and the pattern of dots, then the object is going to scatter only a few of these dots, and the other dots are just going to go into the background, and basically there may be negligible scatter from the background. But whatever is scattered from the object is going to be captured using a CCD array, and the CCD array may be programmed to see this image of dots, the silhouette of these dots, and based on that it will be able to sort of figure out the periphery of the object that's scattering light from here. right? So you can imagine if you want to have very fine features, these dots could be much closer, and then you will be able to make out even smallest of gestures. So this is quite useful, because whenever you are making a gesture from, let's say from here, you're waving your hand over here, then I'm actually scattering a different set of points with respect to this. So and if I can continuously track that movement, then I know that I'm making a gesture from, from one side to the other side. So that is essentially what is happening, and that's how these people are able to communicate with the machine. So in the real world today, we are actually trying to break down the man-machine interface and try to make it easier for somebody to actually interact with machines, and gesture recognition is really at the forefront of this revolution of how this interface is going to happen. So in the future, you can imagine that there will be a lot more machines which respond to gestures from other human beings. So this is actually, there is a Microsoft is a company that has come up with a product. It's called a Microsoft Kinect system, which is used in this Xbox video gaming console. But I believe there are plans from Microsoft to incorporate this into their regular operating system. So the future operating systems have a gesture recognition as part of it. So maybe you don't need a mouse or a keyboard even, that you could potentially communicate with the machine in a rather easier manner, and that is actually enabled through optical sensors, in this case an amplitude modulated sensor. So let's move on to another type of sensor. Now I will go to how a phase modulated sensor might work. A phase modulated sensor, to see how it works, consider this diagram over here. You have light coming into this what is called this 3 dB power splitter. It splits the light into two equal parts, and then it's going to go through some length of fiber, and then it comes to another 3 dB splitter. Here you have mixing of these two intensities, and then the fields corresponding to these two light waves, and then you have a combined product over here as well as here, but just let's focus our attention to what's coming out here. Now what's going to come out here is going to be based on the phase that it accumulates as it's propagating through the structure. So we know that phase, when you're looking at it, is corresponding to 2 pi over lambda multiplied by, where lambda is the wavelength of your incoming light source. N effective is the refractive index of this waveguide, effective refractive index of this waveguide, and L could be the total length that it's traversing. So if you look at the combined product, so the field from both these arms, are they going to beat with each other? And so one of them can be looked upon as a reference arm, and other one could be the measurement arm. I'll tell you why that terminology is important. But when you look at the total intensity that comes into it, it corresponds to the intensity of the individual arms, and then you have a beat component. The beat component, and the key part here is that the beat component is going to have a sinusoidal dependence on the relative phase difference between the two arms, the light propagating in the two arms. And from this perspective, let's say we are interested in the phase that you can get, this is the phase that you want to measure, okay? And so if you're looking at the output intensity is going to fluctuate, but you don't know whether it's fluctuating because of the what you want to measure or because of what's happening in the other arm. So suppose you are keeping this other arm in a controlled environment. So we call that as a reference environment. So it's a fairly well controlled environment. So you know exactly how much is the phase that's accumulated over here, and that doesn't change as a function of time. Then any intensity change because of this component is going to be because of this change in phi 2, that is actually what we call as the measurand arm. So this is actually an example of a phase modulated sensor, and you're not going to be able to do this without this arrangement because of the fact that you may ask the question, why can't I just take this light here and put it through a detector? In that case, all that you'd be measuring is the intensity. The photodiode that you might use to pick up the light, it is not sensitive to phase by itself, right? So the photodiode is actually color blind. It doesn't pick up phase, and also it doesn't pick up polarization. So all it can pick up is changes in intensity. So what you need to do is to convert any phase change here into a corresponding intensity change, and that's why this entire setup, which is called a Mach-Zehnder configuration, that Mach-Zehnder configuration is very important. And it's essentially an interferometer. So what does an interferometer do? It converts phase changes into intensity changes so that you can pick up with regular optical receivers. So where is this useful? Well, this could be useful in a variety of applications. One such application that's very popular is called a hydrophone. So you typically incorporate sensors, say underwater, and you want to track if there are any, for example, enemy ships that are coming, towards you. Since any moving object, any motorized moving object is going to emit certain acoustic signals, right? Those acoustic signals can come and this fiber coil could be exposed to those acoustic signals, in which case it will impart some pressure on this fiber, and due to the pressure, both the refractive index as well as the length are changing ever so slightly. Just imagine, this is actually divided by wavelength, which is in the order of 1 micron. So even if there is a change of in the order of 10 power minus 6 in either of these quantities, you're going to have a fairly huge change in phase. So this is actually a very, very sensitive measurement. So you can essentially in this case pick up acoustic signals, underwater acoustic signals. That's what a hydrophone is, with very high sensitivity. So that's one possible example of a phase modulated sensor. Now another example is what we discussed previously in the case of an aeroplane. We talked about the need for inertial navigation system, and what we are really using there is actually a gyroscope, and in this case it's an optical fiber gyroscope. So what is that principle all about? That's again, once again, another phase modulated sensor. But in this case, what you do is you send the light through a splitter, but instead of going into two separate arms, you actually coil the fiber and bring it back to the same splitter. Okay. So essentially what you are doing is light can come in here, and one part of it can go clockwise, and the other part of it will go counterclockwise. So the path that they are traveling in this case are both the same, and because of that, when they come back and when you look at the output, they essentially cancel each other, right? So the phase difference is between them is 0, and so all the light is just going there. There is no output over here. But suppose you have this coil fixed with a rotating object. If there is a rotation over here, then that actually introduces a relative path length difference between the clockwise and the counterclockwise light beams, and any relative phase path length difference between the two waves is going to create a phase difference at this point, and correspondingly there will be a change in the intensity at the output. So, and that intensity is going to be proportional to the rate at which the rotation happens. So, this is actually a very nice way of picking up rotation, and this is typically not very sensitive to anything else, because any other normal change in the strain or temperature of this fiber, both the waves are actually experiencing that, so they will cancel. So, it is actually a very quiet interferometer, the quietest interferometer that you can find out there, and it's called a Sagnac interferometer. But if it won't change for anything other than just rotation, right? And so it's actually a very, very sensitive measurement of rotation. How sensitive it is? We're talking about 10 power minus 3 degree per hour type of accuracy is possible. So that is actually a very, very small number. So it can give you very high accuracy in terms of the navigation that you want to accomplish. So that's like, once again, another phase modulated sensor. I'm not really talking about the challenges involved here, that I will reserve for future lectures, but this is just to give you an idea of how to use phase changes in light for sensing parameters. In this case, we are sensing rotation. So let's move on to one more type of sensor. Now let's look at how polarization, the light polarization, can be used to sense some physical parameter. Okay, so let's go into what are called polarimetric sensors. To explain this, I'll have to explain something that's called the Faraday effect. So what is the Faraday effect? Well, you can come in with light with a particular polarization, linear polarization, let's say, and it can go through this material which has what is called a very relatively large magneto-gyration coefficient. So what does that mean? In the presence of an axial magnetic field, this material will deflect the light polarization, so it will deflect it through an angle. And the specific way it works is that the response to the incoming polarization is in the fact of epsilon E, which is the normal response to the permittivity, and then it has this other component where you have a curl of the magnetic flux density and the electric field intensity, and that is through this mediated through this gamma, which is the magneto-gyration coefficient. Okay, so some materials exhibit this stronger than other materials. But if you are using one of those materials, it will essentially take this incoming polarization and it will rotate it by an angle theta. And theta can be quantified using this expression, is essentially dependent on the magneto-gyration coefficient multiplied by the magnitude of the magnetic flux density that you are applying, as well as the length of this crystal, right? So longer length means you can have a larger amount of rotation. The interesting part of this is it's a non-reciprocal effect. So what do I mean by a non-reciprocal effect? Reciprocity refers to the case where if you flip the input and the output, you essentially get the same result. Meaning, if I came in with this polarization and this is a reciprocal effect, it goes through a rotation theta, let's say. If I come back with this theta, it will go back to the original polarization. Okay, so that will be a completely reciprocal effect. Now, this Faraday effect is actually not reciprocal. You can get an idea why it may not be reciprocal, because it's actually a vector multiplication of the B with the E field, right? So when you're coming from the reverse direction, you are actually imagine that the magnetic flux is actually against you. So the sign of B changes, and correspondingly sign of theta also changes. So instead of going back to this original polarization, you will end up actually getting 2 times the rotation that you have over here. So this is actually what is called the Faraday effect, and if you can make theta, for example, 45 degrees, if you design this crystals for the theta equal to 45 degrees, you will see that the light that's coming in the reverse direction will go through a rotation of 90 degrees, meaning if you go in with vertical polarization, whatever is coming out is horizontal polarization. So if you put a polarizer oriented vertically, you can extinguish that light, and that's actually the principle for optical isolators. Okay, so you will be able to extinguish back reflected light in optical isolators because of this Faraday effect. But we are planning to use this for a sensor. So let's actually see how it can be used for a sensing application. To see that, let's actually consider a light source, and let it go through a polarizer, so that what's coming out of the polarizer is actually vertically polarized, and then it goes through a certain length of fiber, and then what you have on the other side is actually a analyzer. Analyzer, it's basically, in this case, it's called a polarization beam splitter. So it works such that it will allow the light, vertically polarized light in this direction, and the horizontally polarized light will be deflected. I'm sorry about this. This line should be actually the reverse diagonal. So there's a small typo there, but nevertheless it deflects essentially horizontal polarized light over here. So if you have essentially the polarization maintained in this fiber coil, then all the light would have ended up here, and there won't be any light in optical receiver 2. Okay, but that can change if you introduce a current carrying conductor through the axis of this coil. Okay, so what happens over here, when you have a current carrying wire that's inserted through the middle of this coil, we know that Biot-Savart law and Ampere's law tells you that whenever there is a current going through this conductor, there is going to be concentric generation of this magnetic flux around it. So that magnetic flux now is oriented along the axis of the fiber. And remember the Faraday effect that we just saw, it means that if you have a magnetic flux along the axis of the fiber, and there's a certain polarization that's traveling through the fiber, the presence of this magnetic flux will cause a deflection of the polarization. So the output polarization will have a small component that will essentially register itself in optical receiver 2. So initially, without any current, all the light is going over here, but with a certain amount of current, you will have a certain light intensity that's coming in this port, and if you increase the current through which you are increasing your magnetic flux density, then it will increase theta. Basically that's what we saw over here. So the theta is proportional to the magnetic flux density. So you, with larger magnetic flux density, which is dependent on the current, you have a larger theta, and hence you will essentially have more light in this port compared to this port. And so this could be used as what is called a fiber optic current sensor. So this is actually a very popular device, popular device in the power industry to measure current with very high linearity. We're talking about a linearity of 0.1 amp when you are measuring something the order of a fraction of an amp to even kiloamps of current. It gives you very, very linear response. So that's the power of this particular technology, and that's actually an example of a polarimetric sensor. Now let's move on to the last type of sensor that we want to talk about, which is a wavelength modulated sensor. So far, if you look at what we had been talking about, we talked about changes in amplitude, changes in phase, changes in polarization. Now it's time to consider changes in frequency. And I've highlighted this and for a good reason. Frequency modulated sensors are going to be one of the most rugged sensors that you will find. Why do I say that? Well, if you consider amplitude modulated sensor, just like this one, if you're trying to pick up perturbation over here, let's say it changes the amplitude of light, but before it reaches the photodetector, that might get corrupted during this propagation. Maybe it can get perturbed at some other point, and that is also changing the amplitude and so on. So it can get corrupted. Same thing you can say about the phase or the polarization. But when you consider a frequency modulation, once you have encoded the information that you want in frequency, there is very little that can corrupt that information. Meaning, if, for example, if I take a light source, let's say a laser pointer, a green laser pointer, right? It's emitting at 532 nanometers. You measure across the room and you measure as 532 nanometers. Now you shoot the same green laser to the moon and you measure from the moon what that wavelength is, and that wavelength will still be 532 nanometers, meaning it's that information about that wavelength is not changing upon propagation over very long distances. It's not corrupted in the process of propagating over long distances, right? So from that perspective, wavelength encoded sensors are quite different, and they are quite rugged as well. They're more impervious to noise, if you may want to call that. So let's actually see how a wavelength encoded sensor would work. One example of a wavelength modulated sensor is what we call as a fiber Bragg grating. Now, what is a fiber Bragg grating? We're looking at, say, the core of the optical fiber, which is surrounded by the cladding. If you modify the refractive index of the core in a periodic manner, and that's what we are shown over here. Let's say this direction is Z and this is the refractive index. The core refractive index is normally unmodulated, is like this, but if you manage to create a density variation like this so that the refractive index is periodically changed with a period capital lambda, then you can go back to Bragg diffraction theory, and what Bragg diffraction theory tells you is this will coherently cause interference for light in the opposite direction, and that light whose wavelength is lambda b is going to be reflected from this point. Okay, and lambda b is given by 2 times n effective, which is the effective refractive index of the light that's propagating through this guide, multiplied by period. So if you change the period, you can change the wavelength or the color at which it's reflected. So let's just see what exactly happens. So you can put in broadband light into this fiber Bragg grating, and then what you get at the output, you have one color missing. Where did the missing color go? The missing color actually got reflected Okay, so it got reflected, and so just that particular color, which is defined by the Bragg wavelength, and just a little bit around that is what is going to be reflected. So the why a fiber Bragg gratings? It's all fiber device, so very low insertion loss. There's no alignment required, and more importantly, from a sensing perspective, there is negligible electromagnetic interference for this type of activity. So how can this work like a wavelength modulated sensor? So to understand this, let's consider this sort of schematic. You have broadband light which is going through this device called a circulator. Circulator essentially directs light from port 1 to port 2, but any light coming from port 2 won't go back to port 1, instead it will go to another port, which is port 3. Okay, so when we have a grating in this fiber, when broadband light goes and is incident on the grating, only one particular color of light is going to be picked that corresponds to a Bragg wavelength. And if you see what is coming over here using an optical spectrum analyzer, you will see that the power is actually high at a particular wavelength compared to other wavelengths. Now, how it works like a sensor is through this. If you subject this to some perturbation, let's say you are straining the fiber, right? You're just pulling the fiber. Then what happens is it will essentially change the period. Physically, it will change the period, but it will also, through what is called the strain optic effect, change the refractive index of the fiber as well. So both of these contribute to a change in the Bragg wavelength. So the color is going to change, and by carefully calibrating this change in color, you can basically solve the inverse problem, which is saying, okay, whenever you see so much change in the in the Bragg wavelength, you say that there must have been so much perturbation at this particular point. However, this is where it gets a little tricky. You will find that it's not just strain that can change the Bragg wavelength, even temperature can change that. How? Whenever you heat this grating, there is thermal expansion coefficient which is increasing your period, and then there is actually what is called a thermo-optic effect where it changes the refractive index also. So that's what is actually highlighted over here. This is the thermal expansion coefficient and the thermo-optic coefficient. Both of these also causes, through the change in temperature, it causes a change in the Bragg wavelength. Okay, so whenever you see a change in Bragg wavelength, you don't know whether it's because of change in strain or it's because of change in temperature. So you need to be little careful about that, and these are issues that we will talk about at a later point. But the key takeaway point is that this is actually a wavelength modulated sensor, because now we are looking at changes in wavelength to understand the strength of the perturbation. And the interesting thing is it can be extended to multiple positions or multiple regions of interest. You could concatenate multiple sensors, and this is simply done by having slightly different period for all these Bragg gratings that are inscribed in this fiber, and so each location corresponds to a slightly different color. This is like color coding that you want to that you're accomplishing using this. This is like color coding of mail, or say the dabbawalas, right? They are they are quite famous for the way they handle all the dabbas is by color coding them and making sure that different colors are corresponding to different destinations, and they do a very efficient job of sorting it out. So similar to that, you have color coding of all these locations. So if you see some Bragg wavelength change around let's say green color, then you know that green is the color of the reflection at this particular point, so you know that the perturbation would correspond to this. Whereas if you encoded it this location with red color, any change around the red color can be attributed to perturbation in this location and so on. So you can actually have what is called a quasi-distributed sensing that you can accomplish in this case using wavelength modulated sensors.